Miss Jody here with our next video for the STEAM physics class. We are continuing on. The last video we talked about started talking about the quantum nature of light and how scientists started to think that even though light was having the properties that were consistent with waves, there was one little area that was showing that possibly the wave theory didn't fully fit what we were seeing with light. And I actually made a mistake on this problem back on the notes. You don't have to go back and find them, but just so I'm consistent here. The problem was the photoelectric effect. I don't know why I wrote affect there. The effect, what happens after light is shown onto the particular metal and the current being able to continue on there. So make sure you change that. So when we looked at the part one of the quantum nature of light, we were saying, okay, who was thinking what originally, and why they thought it had the wave-like behaviors and all that, and then who started thinking a little differently. And we spent some time talking about Max Planck and how Planck started to think that light had some properties of what was known as the idea of quanta, discrete packets, so that light, instead of it being continuous, if you were really able to go really, really small, you would see that it was really broken up into smaller parts. And so therefore, changing the way light was viewed, instead of it being a continuous wave, it being in discrete packets. Now, as we move on today, and of course we talked about the black body radiation and how that was showing us something a little differently there than the traditional theories. Moving on today to really understanding the photoelectric effect once Albert Einstein gets into the picture in 1905. Okay, so in the early 1900s, Planck and his formula, E is equal to the h times multiplied by the frequency, his constant multiplied by the frequency. Albert Einstein comes along and starts putting some of these things together, and specifically in the area of light, he combines Max Planck's idea and formula for the energy of these little quanta, these little packets, and then begins to put it all together into the quantum theory of light. So he contributes to that, I should say. All right, so as a review, Maxwell, what was Maxwell thinking? So Maxwell was the one that said, oh, hey, wait, light has to be an electromagnetic wave because the speeds were consistent. I'm going to prop up this little page here, and hopefully that'll make that side not bubble down there because my book is getting so large there. All right, so the speed was consistent, and all the things that they were discovering about electromagnetism, and it seemed to fit the same things that we were seeing with light. So they had the electromagnetic wave theory of light. So the wave theory, and they thought that the waves were continuous. Planck comes along and says, he still thinks they're continuous. He still thinks that's a continuous situation. It's just he thinks that they're absorbed and emitted in quanta. And so that they travel still kind of continuously, but when they're absorbed or they're emitted, they are in these little packets of energy, quanta. And then Einstein comes along, and this is like my drawing. Like if I take a highlighter and I say, okay, Maxwell's idea is that light is just traveling continuous in this electromagnetic wave. Planck says, okay, these little packets, when it's emitted, but then it travels continuously. And then when it's absorbed on this other end, that's those little dots there. It's absorbed in little packets. And then Einstein says, actually, it travels through space as quanta of energy, as little packets, and that if we were able to, bring it up to the scale of the micro for us to see, then we would see it looks continuous, but it's actually these little packets. So what Einstein was doing, along with, Planck, as he was starting to try to figure this out, I think more so Einstein, putting it into the same way of thinking as matter. So at the time, matter is started to be thought of as made of things. So you remember back in the time with Democritus and all that, when he looked at the sand and he said, from afar it looks like it's one big piece, but when you get closer it's a bunch of grains of sand, and he called those little grains granules. When he started thinking matter, all things that have mass and volume, they're made up of smaller parts too, these little granules. So that's when matter becomes chunky, in the sense that it's made of certain things. It's not continuous. But at the time, energy was thought to be continuous, occurring in any amount, no limit to how small an amount of energy could be exchanged between two objects. And so it was this continuous thing. It wasn't really, even though quanta was becoming something that was being proposed by Planck, it wasn't really getting as much recognition until the time of Albert Einstein. And so Albert Einstein then, just like matter became part of the made of things, chunky world, energy became made of things, became chunky in a sense. And so these little quanta, these little packets, he named photons. And of course, even though it became this idea became of these little packets, these little photons for light, it didn't dismiss the wave property of light, because they still knew that there was still frequency, still had a big factor in it. And so frequency, along with wavelength and amplitude and all that, go along with waves. And so when you think of waves, what do you always have? Those four characteristics, main characteristics of waves that we talked about. You're always going to have wavelength, amplitude, frequency, and speed. And so there was still a wave way about light, but then the idea of these little packets. Now there's a visual theory, a visual way of looking at the combination between particle photons and wave-like behavior. And I'm going to send you a video on it, and it actually visualizes this when you have a medium that you vibrate, or a media that you vibrate, and then you put silicon drops on. You can begin to see that the drops will ride along the waves. And I think it's a great visual with the particle behaving like a wave and it's still maintaining wave behaviors. So it's really fascinating, this duality idea. Okay, so, and obviously people think different things, and you have to come up with your own conclusions, because we only know so much, and we just try to look at the behavior and figure out what really is happening and what light really is as a whole. All right, so he begins to think of it as like matter, chunky. So therefore, it's not just continuous. It's made of something, and we've got to find the smallest level of that something, just like we did the smallest level of matter, atoms. Now, of course, since then we realize there's smaller parts to atoms and smaller parts to them, to the making of the protons and the neutrons and all that. But just as a visual, the smaller parts of matter come down to its constituent atoms. And the same thing with energy. The smaller parts of it come down to these little packets of energy called photons. And depending on the frequency and the energy, the frequency is going to determine the energy of the photons. You can have different levels of energized photons. So an electron, in this photoelectric effect, an electron is ejected from an atom when it absorbs a photon of sufficient energy to allow it to free itself from the atom. So you remember on the or the photoelectro effect, when they would have the metal, and I just remember I drew this little guy here. Actually, do we really need to draw that? I'm not. I'll just flip back because it's right there, isn't it? Let me just flip back. Not that that's a good drawing either, but all right. So there's the metal, and the light was shown on it, and then if you had a certain frequency, which would determine the energy, because frequency was related to the energy of the photon, or the packet, the higher frequencies would be able to give it enough of jiggling to free the electron, which we call the binding. A certain binding energy had to be overcome to free the electron so it can move. But if you used lower frequency light like red, it didn't work. But if you used higher frequency light, it did. So there was a relationship in that photoelectric effect. And so when Einstein puts this all together and says all these quanta, these little packets, and then when you have the different levels of frequency, you think of all these little packets hitting, like higher level frequencies, higher energized, and a whole bunch of them hitting, then you would have the ability to overcome that binding effect. And so an electron ejected from an atom, when it absorbs a photon of sufficient energy, it had to be sufficient amount of energy to allow it to free itself. If it was lower amounts of energy, it couldn't do it, like if it was lower frequency. So instead of gradually gaining energy from electromagnetic waves, this was the new way of thinking. So in the old theories of the wave coming at you, if it was just waves, then why wouldn't you just, as long as you kept that light on there forever and for a long time, it would absorb so much of that energy, then eventually would be able to, the electron be able to fly off if it was just a wave. But it wasn't doing that. It didn't matter how much red light you put on. It didn't matter how intense you put the red light on. It didn't work. And so there had to be something else that was working with this situation. And so the idea was, instead of it gradually gaining energy from the electromagnetic waves, there had to be a certain amount of sufficient energy to make it pop off. And so that's when these quanta began to really fit with this photoelectric effect. Then Einstein is able to explain. So energy transfer is done all at one time in this particular theory. Not like I'm gaining so much energy and then eventually I'm broke free. It's you have energized photons, and then when you get the right amount of the right type of photon, energized photon, the right frequency, then boom, it will bust it out. And so when it did that energy transfer, it was kind of quantized, right? So it became what's called a quantum jump. And so it wasn't like over time I've got free, but I had the right amount, so boom, I could bust out. Now on the the photoelectro effect, there were the 4 main points that the book was talking about from the original talking of the the photoelectro effect. And so each one of these that they were noticing, 1, 2, and 3 here, there was a way that the quantum theory actually explained it. So the first one was they were seeing that electrons are emitted immediately when light strikes the photoelectric surface. So what does that tell us? If electrons are emitted immediately, there's no gradual building up. So electrons gain, so in the quantum theory, that's the QT, the quantum theory, electrons gain their, energy, that would be important, gain their energy in single steps rather than gradually gaining energy from a wave. So that, again, quantizes it. So it's these steps, these packets, okay? And that was consistent with what they had seen when they were studying the photoelectric effect. The second thing that they noticed is that high-frequency light causes electrons to be emitted while low-frequency light did not. And so that was the high frequency, closer to blue and all that, or UV or whatever. But the red wasn't working. The red light on the other end, it didn't have enough. Didn't matter how intense you made it, how bright you made the light. And did that fit with the quantum theory? Yes. Photons of high frequency light have more energy than photons of low frequency light. And that is easily brought together with that formula that Max Planck gave us, which is E is equal to the constant, Planck's constant, multiplied by the frequency. So basically, if you have a higher frequency, then those photons have more energy. You see what I'm saying? And so it was consistent with the little packet theory, the quantum theory. And then the energy, number 3, the energy of emitted electrons depends upon the frequency of the light that strikes the metal. So the energy emitted of the electrons, which is the E part of this story, the energy of emitted electrons depends on the frequency of the light that strikes the metal. And that makes sense because we see a relationship already. Light of high frequency has photons of great energy, which makes sense because here's your energy. And if you have a higher frequency, you multiply by the little packet of energy, you're going to have a higher energy. Little packet of quanta, right? So it makes sense. So if you have like a frequency of 5, I'm just using little numbers, 5 multiplied by the little packet, you have a lot more energy than if you had a frequency of 2 multiplied by the little packet. Do you see? So that relationship fit right with the quantum theory and with Max Planck's equation, helping try to understand the simplest amount of the small little quanta, little packets. All right, and then we have number 4, more electrons are emitted for bright light than for dim light. And this also held true in the quantum theory side of things. Why? Because the brighter you make it, so you make it really, really bright, that means you're sending off, that the brightness, the intensity, is the amount of photons, these little packets, hitting the metal. So these little packets, if you send one little packet, it frees and it hits an electron, frees one. If you send 1,000 little packets, it's going to free 1,000 little electrons. So brighter light will equal more photons. It works that way. So the more you give to it, the more it can set free all of those electrons. So the quantum theory was really fitting with this photoelectric effect that was a big problem to the traditional wave-only theory. And so again, talking about the packet side of things. But again, not having to get rid of the whole wave thing, because frequency is a property of waves. And so we still have to bring them together and create a duality. Now, when we start talking about this quantum idea, these little packet idea, it brings us to a little later on the idea that eventually the electron is quantized. And the reason the electron becomes quantized, Niels Bohr in 1913, he started realizing that there had to be these specific areas or specific amounts of energy for the electrons in his particular Bohr model, because of the way that the energy, the light that was spit out in this process of exciting and de-exciting, bringing the electron back down to its ground state. So what that all means is, okay, so think of the electromagnetic theory, the EMT. So in the original electromagnetic theory, which is just the wave theory, right? When applied to the atom, predicted that electrons should continually be emitting radiation because their orbiting motion is essentially a vibration. So if we're thinking about the way an atom is behaving, right? So in the traditional theories, okay, so say this is my little atom, or these are my little protons. In my Bohr model, I've got all of these, flying around, these orbiting electrons. So what they were saying is basically, if these electrons are orbiting around the center of or around the nucleus, because they're having this continual rotation, it's basically essentially a vibration between these positive and negative charges. And just like when we talked about how radio waves work, if you remember how the radio waves are produced, let me see if I can flip back on that page of the radio waves, that radio wave production. Do you remember we were talking specifically about the radio wave production, and these oscillations, these back and forth motions were actually creating this radiation, which would be the radio wave. The radio wave would be generated through this movement, and then it would create the invisible waves that they didn't even know were there, right? And so Niels Bohr is saying, hey, in this same way, we have to look at the idea that the electron would be doing the same thing. We got positive and negative charges that are oscillating. We got all this moving around, this orbital stuff. It would basically be essentially a vibration. And so if it's essentially a vibration, it would be constantly emitting these waves coming off of it, right? The atom. And so when it would be constantly emitting those waves, then would it eventually lose that energy over time as it would continually revolve around the center in its process of its orbiting. And then as it gradually loses its energy, then it would gradually fall in towards the nucleus. And the atom would, explode, die. Because it couldn't just constantly give up its energy. And so the idea was, this can't be right, because there has to be, instead of it just being randomly, all over the place and emitting waves, there has to be like certain levels where the electron can be, and therefore it's stable and not having any loss of energy or any absorption of energy, like a certain area where it could exist and it would kind of be evened out. So he has to put in some assumptions to this model with his atomic model, and trying to unite it with the idea of what they were seeing with the experiments with light and all that, and seeing the energy levels being emitted, as we'll talk about in a minute, in the spectra. So the assumptions were, the electrons that revolve around the nucleus move in specific given orbits. And during that, when they are in their specific orbits, not just this random, vibration and rotation, no radiation is emitted when they are in these orbits. So when they're in their evened out orbit, that's where they belong. It's nice and even. It's not causing it's balanced. But if they are bumped out of that area where they belong, then they're going to be wanting to try to get back to their area where they would be considered stable. So what that means is, if you looked at the Bohr model, and now this sheet I already sent you last week on the other side of the sheet, the diagram, so this you should already have. But in the traditional Bohr model here, so we would have the center, the nucleus, and then we'd have this first area, which we would call like an energy level or whatnot, and then we'd have a second energy level, and then we'd have a third energy level, and so on and so on and so on. The idea would be, as long as this electron would stay in the area where he's supposed to be, which is his lowest level, and he's stable, then there would be no energy emitted. There would be no radiation, what we'd call something flying off of it. But if for some reason you added energy, so you can add energy to atoms, to cause some changes in where their electrons are. You can add heat, you can chemical reaction. So heat, chemical reaction, this is supposed to be a circuit. Electricity, or the absorption of photons that we'll see in the photoelectric effect. And so if you add energy, this electron could be bumped up to an energy level that it wouldn't normally be in. And it would take a lot of that energy to push it up there. It wouldn't just be pushed up for any certain amount. Or just anything. It had to be a certain amount of energy that atom would absorb that would make it fly up to the next level. And this makes sense, right? Because when you start thinking of, say, an electron, and you start seeing like these different levels, eventually, if you get enough energy, right, from all this high frequency, then you would have some bumping up, and then you would eventually have to have or that electron could eventually be flown off of it, right? And so if there'd be enough. But when it comes to the electron being bumped up, if the electron is highly energized from whatever you've added to it, then it wants to get back down to its ground state. And we've talked about this for those of you who take chemistry, and so that ground state is definitely where it wants to be. And so therefore, in the theory, then it would spit out the energy that it was given accidentally by being heated up or whatever, and so that it could get back down to its state. And so what ended up happening is Bohr started to put together this idea of these different levels of energy, and each different level of energy was specific to each different atom too. So that was kind of started creating this like barcode world of each atom had different levels of energy that the electrons could be bumped up to, and then of course going back down to the level they're supposed to be would be emitting this certain types of light. So an atom with an electron in anything but its lowest possible orbit has more than a minimum amount of energy and is said to be excited. So this guy, if he's up here, then he is not at his lowest possible orbit. So he has more than the minimum amount of energy to be balanced out there, and so he's said to be excited. So once the electron is excited, he wants to be de-excited. He wants that to get back down to his low level where it's just where he's supposed to be, and that will come in the process of light emission. So the light, when he spits out that energy, it's thought to be spit out in a photon. Spit out in a photon, and that photon will be specific to how much energy he had to spit out. So if he had to spit out a certain amount, then it's going to come out as a certain color, a smaller amount. If it's a more amount, that depending on how far the jump was, like let's say he's all the way up here and then he's going to jump all the way back down to there, he's going to be spitting out a lot of energy because it took a lot of energy to get him up here when he really belonged down here. Okay, so each time the electron falls, it emits amount of energy that corresponds to the difference in the energy of the levels. So each quanta, each little packet that was once, given to the atom that made it jump up will then be spit out that same amount in the form of the photon. And it will correspond to the difference in the energy of the levels. So what that means is, so say for instance, if I go from 5 all the way down to 1 packet, from my 5 level all the way down to 1, that will be the packet with the greatest energy, because what will happen is all that energy will be spit out, and that would be a very energized situation compared to just going from one level down to one little drop there. Now, this little Bohr model, what I did was I took the numbers inside the book that gave us for hydrogen, and obviously it's not to scale, because if you have this much energy difference between negative 13.6 electron volts or negative 3.4 electron volts, that should be a big gap. And in our book, it shows a big gap if you draw it just flat, if you just draw lines without any of the circles. But just to get an idea of what we're saying here, I just stuck them in there on just a blank Bohr model here. Okay, so let's say my electron belongs there or whatever, but let's say he's bumped up and he is all the way to this 3rd level. Wait, 1, 2, 3, 4. This 4th level. So, wait, no. Yeah, 4th level. And then he wants to be, and then he comes down to the next level below him. Then energy is going to be released if he bumps down to a more stable position, right? So how much energy? Well, what happens is they've figured out these energy levels, and it's kind of complicated using the spectrum lines, but we'll talk about that in a second. But let's just note that if he had negative 0.85 and then he subtracted the amount of energy that would have needed, because that's how much energy it would have been put in to shove him up there, and then if he subtracted that amount of energy that shoved him up there, then that will get him back down to where he's supposed to be. And so you subtract out 1.5 electron volts, and you get 0.66 electron volts. So this gives you the amount of energy that it took for him to originally be shoved up there, and then when he goes back down to where he belongs, it shoots out that amount. So what that means is that these particular amounts have certain quantities to them. They're quantized. It's not just random, like I can fly up here, then fly over there. No, there's certain amounts of energy you need to get up to the next level, or to get back down, And so this gave an idea that each one of the elements, because they all had their own unique levels of their energies, that it was a pattern. So this one specifically is for hydrogen. And what's neat is that the radiation, that means what comes flying off of it when he's jumping back down, is always certain. It will always come off exactly the same. And how we see it, once these photons are, emitted, we will see that when we analyze the visible light. Now, when you're analyzing the visible light, this is, you use what's called a spectroscope, and you're doing a spectroscopic analysis. Spectroscopic. There we go. Spectroscopic analysis. All right, just that so you get your little Miss Jody pronunciation problems for the day. Okay, so how that works is, if you see this particular diagram, if you take regular white light, so just regular light, and which we know that it consists of lots of frequencies, and you shine it through the prism. When you shine it through the prism, it separates and creates a continuous spectrum, and that is your spectrum of visible light, the RIGY-BIV that we always talk about. So regular light going through the prism, continuous spectrum. However, if you take gases, and if you take a hot gas and then you put the light through a hot gas, so at the well, I shouldn't say you put the light, because the hot gas is the one emitting the light, so that's better said there. So the hot gas is emitting the light, because if you take gas and you create it to high temperatures, then it starts doing, the atoms of that starts doing this spitting out the photons, right? So you got this hot gas, the light coming from this hot gas, you put it through a prism, and you're going to see this, what we call the emission spectrum. So the emission spectrum is when you have the black background, and then you have these bright lines of color coming through, showing us the light that's being emitted in the areas specific to this gas. So this particular gas is giving off certain lines, and these lines, we call them bright lines, and they are specific, like a barcode to this particular gas that is being highly heated to put off this light. And so you can then take this code of the bright lines that come through to be able to show that those particular lines belong to whichever gas. Let's pretend like it's hydrogen. So hydrogen's lines, let's say, would look like that in the emission, so the brightness of the gas coming through. Each one of those lines corresponds with a certain frequency of light. And so this frequency of light then corresponds with the areas of the energy levels. And so they were able to put these two things together. And then the same thing with the cold gas is just opposite. So the light is being shined through, so you need a light source on this one, because the gas is not heated up, so it's not putting out light, but you put light through it. And I'll just make this so we know that this is the light source, that's the light source, and that's the light source. So if you put light through the regular gas, it's not heated, and then you take that light shown through the gas in through the prism, it'll split up, and instead of having just bright lines, you'll have the spectrum, but it won't be continuous. There'll be these dark lines in it. These dark lines are called absorption lines. Now, what that means is that, think of this gas here as these Bohr models here. So I got this little gas, and then I'm shining this light onto it, and when I'm shining this light onto it, it's absorbing some of those frequencies, some of that light coming at it, some of the photons coming at it. And so the ones that it absorbs is dark, because it can't come out on the other side, because it absorbed them. And so they say, okay, that this is the absorption, what this gas actually absorbs, which frequencies that are of the light that's being shown at it, of all this, red, orange, yellow, green, blue, indigo, all that, what the gas will absorb certain parts of it, because it depends on the levels of the energy. Meaning you had to have a certain level, remember, to bump it up. It just couldn't be random, like, oh, I put a few in, oh, bump, bump, bump. No, you needed this much to get it up to the next level, or you need this much to get it up to the next level. Well, that much world is that particular frequency on the spectra. So, but it will absorb it because it went into the atom and is creating the bumping. Okay, so this was the idea of the emission, what the hot gas would emit, what it would look like with your bright lines, and then through the gas without it being heated, then the opposite, the dark lines. And then these match. So for hydrogen, they matched. And for sodium or something like that, then it's different lines. And both the bright lines and the dark lines on the emission or the absorption spectrum match. And so it became this barcode of figuring out the levels, these specific quanta areas, these little energy levels where energy is going to have to be either absorbed or spit out to move, was very distinct. And so it kind of confirmed this quantizing side of light. And then for our last point here, then tying this into the quantum theory. So tie in the quantum theory with the electromagnetic theory. If the energy of two photons is different, the two photons differ in frequency. And so light of different frequencies appear as different colors, right? So we know that there's a certain frequency for red light, certain frequency for orange light and yellow and blue and all that when you look at the electromagnetic spectrum. So it makes sense that because depending on how much energy here was needed, it was tied into the frequency of what color would come out. And so it was a joining of the quantum theory with the electromagnetic theory, and it seemed to fit. And so the idea started leaning in that particular way for a duality of light. Now the next topic that we're going to do is finishing up this chapter. We are still on chapter, what chapter is it? 19? Yeah, 19. So for chapter 19, we have one more topic, which is going to just be talking about the types of lamps, the type of lights that we can make. So like the phosphorescent, the laser, the incandescent, and all that stuff, bulbs, so that we can figure out sort of how all these things work in this context of what we are seeing here with the quantum theory of light.